You know that feeling when you're like just staring at a math problem, completely paralyzed,
Well,
and you just want to scream, just show me the steps.
yes, it is the universal desperate plea of students everywhere.
Right.
I mean, it's completely understandable, but, it's also a trap.
It's so tempting, though. Like, you just want the algorithm, the
Yeah.
formula, just the exact sequence of buttons to push so you can finish the worksheet, get the grade, and move on with your life.
Exactly. It feels like productivity.
But welcome to the deep dive. Today, we are looking at a stack of sources. I mean, we're talking massive studies on K-12 mathematics environments, cognitive architecture research, and the actual neuroscience of mistake making.
Which is fascinating stuff, by the way.
It really is. And our mission for this deep dive is to decode that exact classroom frustration. We want to give you, the learner, the ultimate cheat code for understanding how your brain actually learns.
Right, because asking for the steps always feels like the quickest path to success. You feel productive, like we said. But the data from our sources reveals a pretty harsh reality. Copying those steps works, well, right up until it spectacularly doesn't.
Okay, let's unpack this right away. Because asking for the steps and just copying them down line by line, it's a lot like watching a high-intensity workout video from the comfort of your couch.
Oh, I love that analogy.
Right, and expecting to get ripped. You're observing someone else do all the heavy lifting, you're tracking their movements perfectly, and you're, like, hoping the sweat somehow magically transfers to you.
Yeah, but it's actually worse than just using a workout video.
Wait, really? Why?
Because physical muscles at least give you a visual cue of who is doing the work. You can see the other person sweating. Cognitive work is totally invisible.
Oh, that makes sense.
So to understand why copying fails so miserably, we have to look at the traditional I do, we do, you do model of instruction.
Okay, yeah, I remember that from school.
Right. The teacher demonstrates a procedure on the board. The class supposedly does one together. And then you're assigned like 20 identical problems to do on your own.
Standard Tuesday math class.
Exactly. But according to observational data collected from over 400 classrooms, this model often actively prevents thinking.
Wait, hold on. It sounds totally backwards to say a foundational teaching model actively prevents thinking. I mean, what are students doing if they aren't thinking?
Well, when researchers actually sat in these classrooms and tracked student behaviors, they found an entire spectrum of avoidance.
Avoidance, like just zoning out.
Yeah, there is the obvious slacking, where a student is just staring out the window.
Uh-huh.
But then there are the more subtle, socially acceptable forms.
Like what?
There's stalling, which is the sudden, urgent need to sharpen a pencil 3 times.
Oh, yeah. Or suddenly you're dying of thirst and need water.
Right, or obsessively reorganizing your desk. And then there's faking. Yeah, faking is where you stare incredibly intensely at a textbook page, you furrow your brow, you look highly thoughtful, but you are producing absolutely nothing.
Guilty. I have definitely done that.
We all have. But then there's the most dangerous one of all, mimicking.
Mimicking. So playing the role of the human photocopier?
Exactly.
Yeah.
Let's pull a real classroom scenario straight from the sources to illustrate this. A student is learning subtraction with borrowing.
Okay.
They're given the problem 72 minus 69.
Right.
They can perfectly execute this by mirroring the teacher's exact visual steps. They cross out the 7, write a 6 above it, put a little 1 next to the 2 to make it a 12, and then subtract 9 from 12 to get 3.
And then they get the correct answer, 3. So, what is the actual problem here if they got it right?
The problem is they are just hoarding steps.
Hoarding steps.
Right. They haven't engaged with the underlying logic of what they just did, which is physically decomposing a set of 10 into 10 individual ones.
So they're just like moving abstract symbols around a page based on spatial memory?
Exactly. So the second the problem changes slightly, or maybe it's presented as a word problem about buying apples at the store, they crash.
Because the visual pattern is broken.
Yes. They possess what researchers call fragile procedural knowledge. They know how to perform the mechanical action, but they have absolutely no idea why it works.
Okay, hang on. I'm going to push back on this a bit.
Sure.
Because if I go to a basketball court and I shoot 1,000 free throws, I am mimicking a form over and over again, and I get better at basketball.
Right.
Repetition is how humans learn. So why doesn't doing 1,000 subtraction problems work the exact same way? Like, practice makes perfect, right?
Well, basketball is fundamentally a motor skill. You're refining physical coordination and muscle memory. Copying a math procedure isn't a motor skill. It's an illusion of a cognitive skill.
An illusion. Wow.
Yeah. The sources lean heavily into cognitive load theory to explain the difference here. When you just copy, The cognitive demand, the actual mental heavy lifting, stays entirely with the teacher.
So my brain is just coasting.
Right. Your brain is not engaging in what cognitive scientists call the germane work.
Germane work. What does that actually mean for the person sitting at the desk?
Germane load is the productive mental friction required to build schemas. And a schema is like an interconnected network of meaning in your brain.
Like a web.
Yes. It's how you link a new concept to everything you already know. When you shoot a basketball, you are constantly adjusting your schema based on physical feedback.
Right. The ball hits the rim, so I adjust my wrist on the next shot.
Exactly. But when you copy a math problem, you are bypassing the germane work entirely. You avoid the cognitive friction required to weave that new information into your brain.
So copying equals no thinking.
And no thinking equals no learning.
Okay, so the mimicry trap is a behavioral failure. You're dodging the cognitive friction. But let's look under the hood.
Okay.
Because the sources make it clear that learning is not just a passive reception of rules, it's a biological event. Like you are physically building new anatomical structures in your head.
And this is where the neuroscience from our sources completely upends how we view frustration. Real learning requires the physical production of myelin.
Myelin, that's the white matter, right?
Right. Myelin is a fatty substance that physically wraps around and insulates your nerve fibers, your axons.
Okay, so what does that actually do?
Think of a raw neural pathway like a dirt road. Electrical signals travel down it pretty slowly, and they leak out.
Because you lose information.
Yeah. But as myelin wraps around that pathway, it essentially paves the road. It prevents electrical leakage and exponentially increases the speed and efficiency of the signals.
Okay, the million-dollar question for you, the listener, is how do we get our brains to pave those roads? Like, how do we manufacture myelin?
Through cognitive struggle, through attempting something, failing, and trying to resolve the failure.
And this brings us to what I consider the absolute oh moment in the research.
Oh yeah, the ERPs.
Right. So to see this happening, neuroscientists use brain scans looking at event-related potentials, or ERPs, to measure real-time electrical activity. And they discovered that when a student makes a mistake, their brain exhibits a massive spike in electrical activity. It is literally called synaptic sparking.
Synaptic sparking. It's an amazing term.
It is. And the wildest part of this data, that massive electrical sparking happens even if the student doesn't consciously know they made a mistake yet.
Yeah, that is mind-blowing. The human brain is, well, at its core, it's a relentless prediction machine.
It's constantly guessing what will happen next.
Yes. And when the outcome of an action deviates from its prediction, when an error occurs, the brain's error detection network registers that dissonance instantly.
Like an alarm goes off.
Exactly. It fires up, usually within milliseconds, to resolve the conflict. That electrical sparking you see on the ERP scan is the precursor to neural growth.
Wow.
It's the biological signal saying, wait, our model of the world is wrong here. We need to rewire to fix it.
So the subconscious brain is sounding the alarm before the conscious brain even processes the mistake.
Correct.
Yeah.
But here is the catch that ties it all back to the classroom. If you are just copying a teacher's perfect steps, your brain isn't making any predictions.
Oh. Because you're just following along.
Right. And because there is no prediction, there is no error. Because there is no error, there is no dissonance.
And therefore, absolutely zero synaptic sparking.
You are depriving your brain of the biological trigger for growth.
Let's go back to an analogy for a second. Let's talk about driving.
Okay.
Mimicking is exactly like driving in a brand new city with your GPS turned on.
Oh, that's perfect.
The voice tells you to turn left, turn right. You arrive at your destination perfectly. You didn't make a single wrong turn. But if your phone dies the next day, you were completely lost. You didn't build the internal mental map to ever get there on your own.
You were just following the blue line.
Exactly. The myelin, that synaptic sparking, is the physical road being paved in your brain when you are forced to navigate the detour yourself.
It's a very apt analogy. And if we carry that into the bigger picture of cognitive architecture, that road paving process is the only way you achieve automaticity.
Which is what we all want.
Yes. When you engage in the struggle and actually understand the why, the conceptual knowledge, you start to chunk information together. You automate your math facts.
So they become second nature.
Right. They physically transition out of your highly limited working memory and into your vast long-term memory.
Working memory being like the RAM on your computer, which can only hold a few items at once before it crashes.
Exactly. If you were trying to solve a complex algebra problem, but you still have to use most of your mental RAM just to figure out 7 times 8, Well, your working memory overloads.
You physically do not have the bandwidth to process the high-level logic.
No, you don't. By building those myelin pathways through conceptual struggle, you offload the basic calculations to long-term memory.
But you cannot build those myelin pathways by watching someone else's brain do the work on a whiteboard.
Precisely.
Okay, so we know the biology. We know why copying is a dead end. But what does this all mean for you, the listener, when you are sitting at your desk, totally stuck? Because honestly, this sounds exhausting. If struggle is the literal requirement for learning, how do you prevent this productive struggle from just turning into, I quit, I'm just bad at this?
That is the crucial pivot of this whole deep dive. We have to fundamentally reframe your relationship with frustration.
Reframe it how?
The sources are incredibly clear on this point. Struggle is not a sign of inadequacy.
It's not.
No, feeling confused is not proof that you aren't a math person or a science person. Struggle is the mechanism of development. Confusion isn't dead end. Confusion is the starting point.
We need to learn how to operate in what the research calls the zone of proximal discomfort, which is just, I mean, that's a brilliant phrase.
It is the sweet spot. It's the space between being totally bored because a task is too easy and being totally paralyzed because it's impossibly hard.
Okay, so if traditional teaching is breaking our brains, what does a classroom that actually builds myelin look like?
Let's walk into a thinking-based classroom from the sources. Instead of handing out a formula and 20 identical practice problems, the teacher utilizes a low-floor, high-ceiling task.
Meaning anyone in the room can enter the problem, regardless of their skill level. But the problem scales up in complexity the deeper you look.
Yes, instead of writing the formula for volume on the board, the teacher might say, find the dimensions of a pyramid if the volume is exactly 48 cubic centimeters.
Oh, so working backward.
Right. Or they might ask an incredibly open question like, how many ways can you make 6?
For making 6, the low floor is just, drawing a box of 5 and a box of 1. Literally anyone can start there.
Exactly.
But the high ceiling is exploring every possible combination, diving into fractions, negative numbers, algebraic expressions.
And in these environments, the students aren't sitting silently in rows. They are standing up, working in randomly assigned groups on vertical non-permanent surfaces.
Okay, vertical non-permanent surfaces is a very fancy, highly academic way of saying whiteboards on the walls.
Fair.
But why does the vertical whiteboard matter so much?
The psychology behind it is profound. When you ask a student to write in a notebook with a pencil, the permanence of the graphite on the paper paralyzes them.
Because they don't want to make a mistake in their permanent notebook.
They are terrified of writing the wrong thing down.
Yeah.
But because the ink on a whiteboard is inherently temporary, the emotional risk of making a mistake plummets.
The affective filter in the brain lowers?
Yes. Students get stuck. They argue. They draw concrete visual models. They erase them. They try a totally different approach.
It's messy.
Very. They even look over at other groups to borrow an idea, which in this environment isn't cheating. It's called knowledge mobility.
I love that.
They are actively navigating that zone of proximal discomfort.
That sounds like a great classroom dynamic. But again, pushing back here a little.
Okay, let's hear it.
When you are an adult listener, studying alone for a certification or trying to learn a new coding language at your kitchen table at midnight, you don't have a group of peers and a giant whiteboard.
That's true.
So how do you manage the frustration when the struggle gets too heavy?
This brings us to architectural scaffolds. We need to build structures to support our brains when the cognitive load gets too heavy.
Okay, like what?
One incredibly effective method highlighted in the sources is treating mathematics the exact same way we treat writing. It is a routine called rough draft math.
I love this concept because when you write an essay, you never expect the first draft to be perfect.
Right.
The first draft is supposed to be messy. It's a brain dump. You just want to get the ideas out of your head and onto the paper.
But in math, we've been culturally conditioned to believe that if the first thing we write down isn't the final, polished, correct answer, we have failed.
We think we have to see the whole path before we take the first step.
Exactly. Rough draft math explicitly gives you permission to be incomplete, uncertain, or totally incorrect.
So you just start?
You put your initial messy thoughts down without judgment. You draw a terrible diagram. You write a partial equation.
And then, just like an essay, you revise.
Yes. You refine the logic. It fundamentally lowers the emotional stakes of starting a difficult problem.
It kills the blank page paralysis. And there's another routine in the research that stood out for building psychological safety called My Favorite No.
Oh, my favorite no is brilliant. It's a routine where a teacher collects everyone's answers, scans them to find an incorrect one that features a really smart, logical mistake, and then presents it anonymously to the entire class.
But they don't mock it, right?
No, they celebrate it. They dissect it together. The teacher asks, what did this person do beautifully? Where is their logic completely sound? And at what exact step did the logic
It
diverge?
completely removes the shame of being wrong. It sends the message, your mistake is the most valuable data point in this room right now.
Because biologically it is. That mistake is the exact site where the synaptic sparking is happening.
The myelin is being built.
Exactly. By analyzing the error as a group, the whole class is doing the germane cognitive work of repairing their mental models. They're paving the dirt road together.
So let's bring this directly back to you listening right now. We completely validate your frustration.
We really do.
When you are staring at a complex problem, feeling completely stuck, it is biologically normal to want the quick fix, to want the easy steps.
Right. Your brain is an organ trying to conserve energy, and thinking burns a lot of energy.
But you have to remind yourself that taking that shortcut, just looking up the answer key or asking for the algorithm, it robs you of the physical brain growth you need to succeed long term.
You are skipping the heavy lifting.
You're riding in the passenger seat with the GPS on, hoping you'll magically know how to drive the route tomorrow. It won't happen.
No, it won't.
The core takeaway here, the ultimate cheat code, is a total shift in your identity as a learner. Your job is not to be right immediately. Your job is to think.
And thinking is inherently messy. It is fraught with errors. But those errors are quite literally the sound of your brain getting stronger.
Before we wrap up, there is one final, incredibly provocative thought from the sources that we have to share, because it flips everything we just talked about on its head.
Yes, this is the paradox.
We talked a lot about the goal of automating your knowledge, right? Chunking information together into long-term memories so you can solve things quickly. But there is a massive flip side to this called the insight paradox.
The insight paradox is fascinating.
Huh.
It turns out that sometimes experts become too automated.
Too automated.
Yeah. Their brains have clumped information together so tightly that when they are faced with a truly novel, creative problem that breaks the rules, they completely freeze.
Okay, to show you how this works, we're going to do a live experiment.
I'm ready.
Okay, I want you to imagine the Roman numeral 7, VII. Okay.
Got it.
Now imagine it's made of matchsticks. 2 for the V and 1 for each I. 4 matchsticks total. I am looking at a puzzle from the sources right now. The rule is you can only move one single matchstick.
Okay.
Move one matchstick to make the number 1.
Oh boy. Try to solve it.
Seriously, I'm trying. VII. If I move the final I to the front, it becomes IVI. That's not 1.
Nope.
If I turn the V into an X, that's 12. I'm totally stuck. My brain just keeps seeing a 7.
And that is the insight paradox in action. Your brain has instantly and automatically chunked those matchsticks into the rigid concept of the Roman numeral 7.
I literally can't see it as anything else.
Right. To solve the puzzle, you have to perform what cognitive scientists call chunk decomposition. You have to mentally break that solid 7 back down into its raw, meaningless components.
So just 4 pieces of wood.
Exactly. Just 4 sticks.
Okay, wait, what is the actual answer? I have to know.
Okay. Take the right side of the V and lay it horizontally across the top of the 2 I's.
Oh, wow. It forms the mathematical symbol for a square root. The square root of 1, which is 1.
Yes. The experiments show that the tighter the chunk in your brain, the harder it is to break it apart to see a new creative solution.
So the experts were too locked in.
The experts in these studies literally couldn't see the individual matchsticks anymore because their automated procedural knowledge was blinding them.
That's wild.
It requires a massive creative breakthrough to dismantle an automated schema. It's a phenomenon called constraint relaxation, where you have to temporarily let go of all the rigid rules you've memorized just to see the problem fresh.
So if you are currently sitting there, staring at a problem, feeling terrible because you don't have the steps memorized and everything feels slow and clunky, don't feel bad.
Not at all.
Your lack of automation might actually be setting you up for a creative breakthrough. Because you aren't blinded by the rules yet, you might see a completely novel solution that someone who just perfectly memorized the algorithm would entirely miss.
Yes. Your confusion is keeping your mind flexible. It is a feature of the learning process, not a bug.
That is definitely something to mull over the next time you're stuck. So the next time you find yourself reaching for the answer key or begging someone to just show me the steps, remember the couch and the workout video.
Get up and do the reps.
Exactly. Grab the heavy weights. let the dissonance spark in your brain because the struggle isn't in your way, the struggle is the way.